All right, y'all. So welcome to organic compounds naming exercise. We're gonna just go through every single question. It's gonna be a very long video. Skip to what you need, figure it out, go at 1.5 speed. Don't really care. Let's just do this and understand why we name all of these things the way we name them. So looking at our number one compound, I notice that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. 10 carbons is dec. This one is going to be decane. Decane. There's no ene or ine because it's all single bonds. Moving on to number two. Number two. Similarly, we have two carbons. So two carbons is F, but this time we have a triple bond. Triple bond is ine, ethine. Moving on to number three. We have one, two, three, four carbons. So that's going to be bute. And we have a double bond, but only one double bond. So we're going to say butene. Now we have to symbolize where that double bond is. So we're going to say one butene. You could also say bute, one ene. Both are going to be acceptable. You'll have to recognize both. All right, moving on to number four. Number four, we now have 1, 2, 3, 4, 5, 6, 7, 8, 8 carbons. So that's going to be oct. Oct. We have a couple double bonds. We have 1, 2. So this is going to be octadiene. Octadiene. And these are on the 1, 2, and 3 carbon. We always want to use the lowest numbers. So we're going to say 2, 3 octadiene or octadi-2,3-ene, but I'd rather put the 2, 3 in front, honestly. That's my preference. Number 5, we have one carbon, simple structure, methane. No double bonds, no triple bonds. Number 6, also quite a simple structure. We have 5 carbons here. 1, 2, 3, 4, 5. We're going to call this one pentane. Number 7. Number 7, we have to check. 1, 2, 3, 4, 5, 6. This is going to be hex. Hex. And we have, let's see, 1 triple bond, 2 triple bonds, 3 triple bonds. So hexatriene. Hexatriene. Hexa. Oh, triene. Triine, sorry, hexatriene. And these are on carbon 1, 3, and 5. So 1, 3, 5, hexatriene. All right, moving on, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The IB doesn't need anything more than 10, which is dec. 12 is dodec. Like a dodecahedron is a 12-sided die, but this is dodeca, and we know we're going to have some double bond action. So dodeca something ene. This is dodeca diene to reference the 2, di meaning 2 double bonds. And we could look at either carbon 1 and carbon 3, or if we go from the other end, it's going to be carbon 11 and 9, but we want 1, 3 dodeca diene. All right, moving on to number 9. I'm going to try and go through these as quickly as possible, the early ones. 1, 2, 1, 2, 3, 4. That's going to be bute. We have a triple bond. That's going to be butine. And butine, we know that that is going to be on the first carbon, 1 butine. Over here, we now have 1, 2, 3, 4, 5, 6, 7. 7, the word is hept. Hept with a P. And we have how many double bonds here? 1, 2, 3, 4, 5, 6. 6 is hex, so heptahex. Heptahex. And that is going to refer to the double bond, so hexene. And then we have to count where they are. Turns out they're on every 1, 2, 3, 4, 5, 6, 7. They're on every single carbon. We don't count the 7th one because the 6th one represents it. So we can just say 1, 2, 3, 4, 5, 6 heptahexene. Now, it's weird because you theoretically could just say heptahexene because there is no other place for those enes to go. You cannot put those double bonds anywhere else. All right, moving on to 11, a little break from the hardness. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's going to be that's going to be nonane. Simple enough. Now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Again, we have that dodeck, but this time we have one double bond in the beginning. So it's going to be one dodecaene, but we can't say dodecaene. So we actually just drop this A and it becomes dodecene. You generally don't like that weird double value unless you have tri and then triene, diene. But dodecaene, it's dodecene. I think that's in your cognity chapter about IUPAC naming. All right, moving on. 1, 2, 3, 4, 5, 6, 7, 8. That is going to be oct. So we're going to say oct, and we have one triple bond right here. So octine. Now we're going to have that on the carbon 1, carbon 2, 2-octine. All right, moving forward, we've got 2 carbons. That's ethene, and that's just ethene. There's nowhere else for that bond to be. We don't have to say 1 ethene. It can't be anywhere else. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's going to be dec. And we know that there are double bonds here. So we have 1 double bond, 2 double bond, 3 double bond, 4 double bond. So 4. Now with 4, we don't use the carbon prefix of but. We use a numerical prefix of tetra, like tetrahedral. So this is going to be decatetra, decatetrine, decatetrine. And that's going to be on carbon 1, 2, sorry, not 2, carbon 1, 3, 4, and 5. 1, 3, 4, 5, decatetrine. All right, moving on to number 16. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's going to be non-9. We know it's going to be non-ine because we have this triple bond right here, smack dab in the middle. This is on carbon 1, 2, 3, 4. If we count from the other end, it's 1, 2, 3, 4, 5. So we're not going to use that counting. We're just going to say 4 non-9. All right. Moving on to number 17, we have a double. We have 2 triple bonds. One here, one here. So we know that we're going to end in diene. All right. How many carbons do we have? And you'll notice I keep doing this from different ways because whatever works with you, I want you to use that method. I'm going to just do this in different ways until you find a method that works for you. Looking at the carbons, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11. 11, again, the IB is not going to ask you for this, but that's undeca, like undeca, like UN. Undecadiene, and those are on. We can count the carbons. Let me just change the color. 1, 2, 3, 4, 5, 6, 7. So it could possibly be 2, 7, or 1, 2, 3, 4, 5, 6, 7, 8, 9, or 4, comma 9. We're going to use the 2 comma 7. 2 comma 7 undecadiene. All right, moving to our first cyclical structure. When we have a cyclical structure, we have to add the prefix cyclo. So this circle is going to add the prefix cyclo. And we have 5 carbons. 1, 2, 3, 4, 5 carbons. So that's going to represent cyclopent. And then we have triple bonds, or double bonds, sorry. So that's going to be cyclopentadiene. Now we just have to count them out. With circular structures, you just count wherever it's going to be lower. Sorry, this is pentadiene. We don't say, we got to keep those vowels in between our consonants. So I can count 1, 2, 3, and I think that's going to be the shortest. So I'm going to say 1 comma 3 cyclopentadiene, because I always want to use the least amount. I see on 19 we have 6 rings, which we could just say, we could say cyclohexene. Hexene, actually, sorry, this is not cyclohexene. This would be cyclohexatriene. But the issue with that is this structure actually has a common name called benzene, which, while chemically is represented by that, we should theoretically put a circle in the middle, because this is not double and single bonds with resonance. This is actually single bond with this shared delocalized extra electrons moving around. But this one's benzene. You should be able to recognize it. Moving on, I see a cyclical structure. So I'm going to say cyclo, and I see 1, 2, 3 carbons. So I'm going to say tri, and then lastly, I see a double bond there. So I'm going to say triene. There's only one double bond, so we can just say 1 cyclotriene, but oh, sorry, I am just getting all mixed up on this one. I'm getting my prefixes confused. This would not be triene. We're talking about the carbons. This would be propene. You got to make sure that you stay with it. Cyclopropene. Triene would reference 3 double bonds, but we only have 1. You might want to say 1 cyclopropene, but in this molecule, first of all, by molecular geometry, you can only have 1 double bond. But regardless of that, no matter where you put that double bond, it will always be 1 cyclopropene. So we don't need to worry about that. All right. Moving on to 21. We've got this weird structure here, but if you count it out, you have 1, 2, 3, 4, 5, a total of 6 carbons. So you have 6 carbons. There are no double bonds, so it's going to be cyclohexane. So for 21, you're going to see a cyclohexane. Cyclohexane. Nothing special about it at first thought. For SL, don't really worry about it. But for HL, we would actually look at this structure, because you can have 2 structures that this cyclohexane can make. It can make a boat or a chair, because that's kind of what it looks like from the side. This is the chair structure. These are 2 different structures. These are structural isomers. So just, you want to be wary that these 2 isomers exist if you're in HL. Moving on to 22. I notice that there are 1, 2, 3, 4 in a cyclical structure. So that's going to be cyclobute, and we have cyclobuta, and we have 1 double bond, 2 double bonds, cyclobutadiene. And where are these located? They are located on the 1 and 3 carbons. No matter which way you go, it's going to be 1, 2, 3. If you go from any other direction, 1, 2, 3, it's always going to be 1, 2, 3. All right, moving forward. This one's going to get a little wonky now that we have these extra structures. I notice a 5-carbon chain. Now, you might say this is pent, and you might be right. You actually would be, because what we have here is an F, and what we have here is a meth. So let's start out with our base chain. I'm going to use black to represent the highlight in yellow. So we have a pentane. Off that pentane, we have a methyl group, methyl. So this is a methyl pentane, and that is on the 3rd carbon, 3-methylpentane. I should give myself a little bit more room. Off that 3-methylpentane, we also have a 3-ethyl. 3-ethyl, 3-methylpentane. The reason you put ethyl before methyl is alphabetical. That is the way it works. I know. Now, moving on to 24, this is where it can get a little confusing. You might initially see this C3H7 as a side chain, but when compared to this carbon over here, it's 3 carbons versus 1 carbon. So what we actually have to realize is we have C3, 4, 5, 6. We actually have a hexane here. So we're going to start with hexane. Off that hexane on carbon 1, 2, 3 from this direction, let me switch colors. 1, 2, 3, we have a methyl group. So this is going to be 3-methyl hexane. Make sure you watch for those little side chains, because when they put that C3, you can assume it's a chain of 3 carbons. Quarter of the way there, y'all. We can move forward. We have what looks like it's actually complicated, but really is just 3 carbons. So we can go ahead and just call this propane. Call it like it is. Oops, can't even spell that. Propane. Moving forward, this one is again trying to trick you. 4, 5, 6, 7 carbons. We also have 2 carbons right here. So regardless of which way we go, we could go 4, 5, 6, 7. So on this one, we have to recognize that we initially have a heptane. And I'm just going to use the green to represent that methyl group that is on the 3rd carbon. So it is 3-ethyl heptane, 3-ethyl heptane. And with this one in particular, just be careful that you're making sure everything's on the right carbons. And I gave myself too much room. This should all be one word. By the way, these should all usually be one word separated either by commas or hyphens. Moving forward, this one we get a little bit back on track on kind of the less crazy side. We have 1, 2, 3 carbons, and regardless of which direction we go, we continue with one other carbon. So I'm just going to kind of put it right down the middle, just to give us a little sense of consistency. That is a butane. On this butane, we have 1 methyl group and a 2nd methyl group. This is going to be dimethyl. Dimethyl, and these are both on the 1 2nd carbon. So this is 2, 2 dimethylbutane. All right, moving on back to our cyclical structures. 1, 2, 3, 4, 5, 6. Oh, look at this. This is benzene again. Once again, we have a benzene. Off this benzene, we have 1 methyl group, 2 methyl group, and we have a propyl group. Now we have to go through LMNOP. So methyl is alphabetically first, but I'm just going to actually write this from the backbone. The red is the benzene. Then methyl is going to go before propyl. So propyl will attach to the benzene. So this is going to be propyl. Oops, put that YL backwards. Propyl. This is going to be propylbenzene. And let's do our count. We can do 1, 2, 3, 4. And that's going to be 1, 3, and 4. We can maybe go from the other side. 1, 2, 3, 4, 5, 6. That would be 1, 4, and 6. These are for these are for those extra groups outside. I don't really like that. We could go from the propyl group and count again 1, 2, and 4. We are actually going to take the 1 and 3 so that our first numbers are actually smaller than our second number. That methyl, again, is going to get priority, just like it does in the order of the wording. So I'm going to go ahead and with our methyl group, I'm going to use black for it, 1, 3 dimethyl. Then I'm going to go, oops, back to green, 4 propyl benzene. Moving forward. That was probably one of the hardest ones yet. I noticed 2 carbons. This is going to be Fn, because it's all single bonds. But now we get our first real functional group, the OH. That is an alcohol. This is going to reference FN all. No matter where you put that OH, it's always going to be on the end. There's only 2 carbons. There's no other way to do it. Moving on to our next one. Oh, want to use highlighter. This is going to be propane. And there are 2 alcohols this time, but we'll start with our propane. AN to reference that this is all single bonds. On those single bonds, we have 1, 2 alcohols. This is going to be propan diol, and that's on carbon 1 and carbon 3. 1, 3 propan diol. So that's with our functional groups. The next one is going to have even more. All right, so for this next one, once again, we have to recognize the initial carbon chain, which 1, 2, 3, 4, 5. So this is going to be pentan. Pentan to represent the single bonds, AN. But now we have many different alcohol groups. We have 1, 2, 3, 4. So this is going to be pentantetrol. Pentan, nope, let's go to our writer. Tetrol. OL. Not pentantetraol, tetrol. We don't want that double value or double vowel. Tetrol OL to represent the OHs. The shortest number is 1, 2, 3 instead of 1, 2, 3, 4. So this is going to be 2, 2, whoops, 2, 2, 3, 3, pentantetrol. All right. So moving on to number 32. Once again, we're going to count the initial carbon chain. This is 1, 2, 3, 4, 5, 6 carbons. So that's going to be hexan to represent the single bond nature of this. And we have 1, 2, 3. So hexan triol. Hexan triol. And these are all actually going to be on the 1, 2, 3, 4, 5, 6, either 1 or 6. So we're going to say 1, 1, 1 hexanitriol. And sorry, much like this last one, I believe I also made a mistake. We don't want those 2 vowels, so we're just going to throw hexane, pentanate, pentanatetrol, hexanatetrol, hexanatriol. Gosh, pronouncing them just gets so difficult as we move to these weird combinations. All right, moving on to 33. It's a cyclostructure. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is going to be a cyclononan. Cyclononan. And we only have one OH group, fortunately, on this one. So this is going to be cyclononenal. Nonenal. And we're not going to throw that E because we don't need to put a vowel because we already have a vowel. There's no point in putting a 1 because we only have one OH group. So regardless, no matter what you do, it would be one cyclononenal because there's only one OH group. All right. Moving forward to another one with a bunch of OHs, we have, I'll stick to blue for the original train, 1, 2, 3, 4, 5. Pentane. I know I'm going to have two OHs, so I'm just going to get that so we get the double vowel, or we get the vowel between the consonants. We have 2, so that's going to be pentanediol. On that pentanediol, we are on carbon 1, 2, and 3. 2, 3, pentanediol. All right, moving to this one. Once again, we have a cyclostructure. 1, 2, 3, 4, 5, 4 carbons. This is going to be cyclobutanol. This is odd because we are both combining the skeletal structure with the written out structure. So we have to take into account that these intersections are in fact carbons. So this is going to be, oh gosh, cyclobutan. And I know I have 3, 1, 2, 3, 3 alcohols. So it's going to be much like the other one with 3 alcohols. Butane let's keep our colors consistent. Butanotriol. On this butanotriol, I noticed that we have 1, 1, and 2. So 1, 1, 2 cyclobutanotriol. Cyclobutanotriol. I'm gonna just fumble over all these pronunciations, and that's okay. Your IB exam is not verbal, it's written. So as long as you write the stuff, you don't have to pronounce it. All right, moving on to 36. 36 has a couple different answers, but you actually have to recognize one of the weird things. You would normally see this benzene ring and be like, chill, it's benzene. But when you have a benzene ring with an OH off the end, we actually start using the term phenol. Phenol. And that phenol is going to represent that whole chain. So I'm going to keep the colors consistent. Off the phenol, we have this ethane or ethyl structure. And we start counting on our phenol from the OH. So this is always going to be our 1, 2, 3. This is going to be 3 ethyl phenol. 3 ethyl phenol. Bring those together. Make it one word. So we have to continue to recognize these structures. All right. Moving forward to a new functional group. We have this O smack dab in the middle of 2 carbon chains. We're actually going to see the same thing over and over and over again here. With this functional group, these are ethers. We're going to start looking at ethers, so I'll just kind of put that out here. There's 2 ways to name ethers. We can say something oxy and then the other group, like methoxy, butane, ethoxymethane, whatever. We can do something like that. We can also just put the name together like ethyl methyl ether. Get the 2 groups and the ether is your base. I'm going to name them with the oxys on some and the ethers on others so you can see both naming conventions. But really what you have to do is, first off, you have to recognize what the chains are. We have a prop and an eth on this one on 37. When we do this, we try and put the shorter chain as the oxy. So we usually want to try and put the shorter chain if we're using the oxy format. So we might say ethoxy propane. Let me actually rewrite this so the oxy's in a different color. We'll use red ethoxy propane, so we can also use red for the ether. On this one, I will use a different naming convention. I'll use the ethyl methyl. In this case, we're actually using dimethyl 2 because we have two methyl groups, dimethyl ether. You can use that here. If you want, you could, I guess, say the other naming structure could be methoxymethane. I prefer dimethyl ether. Honestly, write what you want as long as it's conveyed that this is an ether and someone can recognize it as an ether. Use a structure that works best for you. Something of note is when you are writing the ethoxy, you actually do have to reference the carbon that the ethoxy, which is the ether, is attached to, which is going to be 1 because it's the carbon at the end, which is always going to be 1. So for methoxymethane, doesn't matter because you have two meths, two single carbon structures. But as we move over to, for example, number 39, I'm going to actually do this in different sections. And it's kind of like the better way to look at it. Look at the shorter carbon chain as the functional group attached, almost as if it were an OH, like a weird side chain. And then look, and I use blue for the backbone, the larger chain as the backbone. And in this case, it kind of makes a little more sense for naming because our backbone is just butane. Attached to our butane on the one location, we have one methoxy. And that kind of helps you maybe see it in a different light. So if I were to actually go back and rewrite this first one, our propane is our backbone, propane. We have a propane backbone. And our ethoxy is the functional group attached. You can do whichever way you want. You can look at it whichever way you want, just whatever works best for you. Continue with that structure. Here's where we kind of get a little crazy with it. Number 40, we're going to attach it to a structure. So now I'm going to go ahead and look at my base structure as this benzene ring. So I'm just going to end with our backbone of benzene. And now it kind of helps to look at it that way because we have a functional group. This functional group is a propoxy. So we are going to go ahead and write propoxy benzene. Furthermore, this is on the first carbon, 1-propoxy benzene. We'll take that into number 41. Again, we have our benzene. Sorry that I can't highlight a hexagon. And this time, our structure is this cyclopropane. So for this cyclopropane, we're going to say, going to keep it green, green, 1 cyclopropoxy. 1 cyclopropoxy benzene. Honestly, with this structure. You don't have to write the 1 either. It's, there's nowhere else for it to be because anywhere on this is going to be a 1. That's the difference with these chains. So the reason I'm saying you don't need to write a 1 is because on butane, if we had a butane structure as the previous one, here's our butane structure. You could theoretically see your ketone coming off here, and that would be a 2-methoxy butane. And so here you really do have to specify the number. While in a cyclical structure, there is no middle. Every single one is going to be a 1. So you want to take that into account as you're naming these. Yeah, try and keep it as consistent as possible. Moving to 42, we have our new functional group. This one, double bond O around a carbon. That is a ketone. This is going to reference a ketone. So we're going to just keep on working from that. We have 1 carbon, 2 carbon, 3 carbon. So with 3 carbons, this is called propan, all single bonds, propanone. Propanone. You might say, well, Mr. Garcia, why is it not 2-propanone? Because a ketone always happens in the middle. A ketone's always in the middle. If we put at the end, this is no longer a ketone, this is an aldehyde, and therefore we would name it differently. Because it's in the middle, it is a ketone. Moving on to our next one, 43. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. This is going to be nonane. Nonan, and nonano. However, because there are many middles, we do have to reference where this is. This is on carbon 1, 2, 3, 4. That will be the shortest. 4 nonanone. Moving on to 44. We are mixing a bunch of different functional groups here. So I'm going to start off with the backbone, the biggest chain I can. 1, 2, 3, 4, 5, 6, 7, 8. I could go up for 8 as well, but regardless, it's the same. Octan, and it's going to be octanone. Oops, I'm going to keep that in green. Octanone, and that is, oh, want to keep my colors consistent. Octanone. Now, with this octanone, we have a couple other things, but really quickly, I'm going to note that that is on the 1, 2, 3rd carbon, 3-octanone. All right, now to deal with all the other things. 1-methyl group, 2-methyl group, 3-methyl group. So I recognize I'm going to have a trimethyl. Trimethyl. This is on carbon 2 and carbon 4. So 2, 4, 4, trimethyl 3-octanone. All right, that was quite a long one. Moving forward. You can also, by the way, even though I don't keep saying it, you could say trimethyl, just kind of continuing, trimethyl octan 3-one, and you may see that in the IB as well. It's still going to be it's still going to be in front. You're still going to have 2, 4, 4 trimethyl octan 3-one. Do what you want. As long as you can recognize that these two mean the same thing, you're okay. All right, moving forward, let's recognize our backbone. 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbon. We have a pent. Gonna keep it in blue. Pentan. Pentan with 2 ketones. Dione. Pentandione. Pentanedione. Ketones are actually kind of weird. So instead of pentanedione, this time we're going to get rid of this N. And it's going to be pentadione. Could be pentadione, but this is all singular, all single bonds. I'm going to go ahead and highlight 1-one, 2-one, and this is going to be on the second and third carbon. If we count 1, 2, 3. 2, 3, pentadione. Moving on to 46. Again, this one's going to start trying to mess with you using the C2. So it's a little difficult because we have a C2 up here, a C2 here, and a C2 here. So because of that, it doesn't matter which direction we start our train. I'm just starting right here. 2, 3, 4, 5, 6 carbons. This is going to be hexane. Hexane, and it's going to be an one. We only have 1 ketone. Hexanone. Again, we want the shortest counting. So I'm just going to start from here. We have 2, 3, 3 hexanone. Okay, how the heck do we deal with these 2 ether groups? Or ethyl groups, my apologies. Ethyl, ethyl, so we have diethyl. This is going to be on carbon. Therefore, if that was 3, this is going to be 4, 4, 4, diethyl, 3 hexanone. 4, 4 diethyl, 3 hexanone. Moving on to 47. Finding my backbone. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Geez, this is going to be a decane. So I'll go ahead and write deca because I have ether groups. Much like I did with penta, instead of pentadione, this is going to be also not decane-dione. This is going to be decadione. So I'm looking back at 45 for reference. Decadione. I know if I count 1, 2, 3, 4, 5, I have 4, 5 decadione. Attached to that 4, 5, I have this one methyl group on carbon 3. So it's going to be 3-methyl. 4, 5 decadione. All right. Moving on to 48. Something nice and simple. You might, after you have just done a million ketones, want to say this is a ketone. But a ketone needs to be in the middle of 2 other carbons. This is not in the middle of 2 other carbons. This is on the last carbon. It's also on the first carbon. I alluded to this earlier, but we have a CHO. Specifically, this chemical formula is HCHO, not COH. This is definitely going to be an AL because this is an aldehyde. Aldehyde, which we represent with AL, unlike alcohol, which is OL, and aldehyde is AL. So this is going to be methanal. Methanal. All right. We are into the world of aldehydes. You'll notice this is structured, so you only get 1 formal group at a time, 1 functional group. 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbon. 5 carbon. With number 49, let's look at pentanal to reference that we have an aldehyde. You'll notice I do not need to put 1, 2, 3, 4, 5, 6. Who cares? It doesn't matter because an AL has to, by definition, be at the end. Also, because of that, we're going to actually reference this as the one that has it as carbon number 1. So pentanal is going to be carbon number 1. So I automatically know when I do my counting for later, this is going to be 1, 2, 3, 4. So that really helps out when I go ahead to do this methyl and methyl group, our dimethyls. This is going to be 4, 4, dimethyl pentanal. 4, 4, dimethyl pentanal. All right, moving on to 50. We are halfway through. Well, not really halfway through. We are kind of halfway through. Hopefully I'll be doing less teaching and more just recognizing. Oh, look at that. This is your favorite structure. It's a benzene ring. Now, the wild thing is on our benzene ring, you'll notice we have this protrusion. This is one of those weird cases. Right there, I see my aldehyde. And by definition, the aldehyde on a benzene ring must be on an external carbon. Because if we put a double bond O in the middle of the benzene ring, which cannot happen, because just a quick little explanation, if we look at a benzene ring and we'll just look right here, this is already 1 bond, 2 bond, 3 bonds. A carbon cannot make 2 more bonds. That's not how that works. So we cannot have a ketone on a benzene ring either, unless we attach it to an external structure. So maybe you could have a carbon, ketone, carbon. That's fine. And then another carbon, I don't know, whatever. But when we have an aldehyde on a benzene ring, that as its structure on its own is the only way it can happen. So this is benzenal. That blue all represents our benzenal. On that, I see, oh, I'm going to use our colors. I see right here an ethyl group, and I see all the way over here a butyl group. Now, when we're deciding between butyl and ethyl, butyl is going to be written first because B comes before E. We're back in that alphabetical order scheme. So this is on carbon 1, 2, 3, 4. I know I'm going to be going around that way because once again, aldehyde is carbon number 1. And I have to go around in this direction because then I know I'm going to hit this group as well, and therefore I'll have the lower numbers. You could try it. If this is 1, 2, 3, 4, 5, 6, oh, that's so high. We could just go 1, 2, and 4. Then our numbers are 2 and 4. All right, so this is going to be 4 butyl. Then 2, oh, I should change colors. 2 ethyl. 4 butyl, 2 ethyl, benzenol. Benzenal, sorry, AL, benzenal. All right. So for this one, we once again have to remember that our aldehyde is going to be carbon number 1. So starting with my backbone, I have 1, 2, 3, 4, 5 carbons. So this is going to be pentanal. The only issue this time is I have a triple bond right here, and it's going to be on carbon 4. Because if I go 1, 2, 3, and 4. So this is going to be 4 instead of pentanal, it's going to be pentyne now. 4 pentyne now. So we just have to make sure we get that triple bond carbon there. All right, moving forward. This one's going to be quite complex. We're not only recognizing the longest chain, but we're trying to put that aldehyde in that chain. So while we do seem to have a 5, 6, 7, 8, 9 chain here, it does not in fact include this aldehyde, which we can only reference the aldehyde as an Al at the end of our chain. So we're going to have to actually look at what we call our chain. So instead, we're going to go 5, 6, 7, 8. So instead of a nonane, we're going to have an octane. So my base is going to be octanal to reference that aldehyde. And again, that aldehyde is carbon number 1. So as I count, this will be 1, 2, 3. And then we have a couple groups attached to this. So I notice that we have 1 ethyl group, 2 ethyl group, diethyl. I also recognize that I have a methyl group. Eth comes before meth alphabetically, so I'm going to start out with 2, 3 diethyl. Then move on to my methyl group, 3 methyl. So 2, 3 diethyl, 2, 3 diethyl, 3 methyl octanal. Oof, that was a wordy one. All right, moving forward. Again, we're going to have this clash. You see this cyclo group right here, which you want to automatically make your longest chain. That cyclo is really appealing to talk about, but you can't really have that aldehyde there. Furthermore, we can make just an equally long chain because we have 4, 5, 6, 7 carbons right there. So I'm going to actually start off with this heptanal. Nice and easy chain right there. And then on that heptanal, I can recognize a cyclobutane chain. And so I see this cyclobutane over on carbon 1, 2, 3. So this is going to be 3 cyclobute. But the issue once more is this is still a butyl chain, so 3 cyclobutyl heptanal. 3 cyclobutyl heptanal. Remember, this YL shows that this is a side chain. It's kind of weird because that's the first time we're seeing a side chain attached to the main chain that is also a cyclo structure. All right, moving to 54. I see 1, 2, 3, 4, 5, 6. Oh, and I noticed something different here. Now, we do see an aldehyde, but we also see an alcohol. The aldehyde and the alcohol together makes a new formal group. This new formal group is an carboxylic acid. Oof. So with this carboxylic acid, which is also much like the aldehyde, going to take that carbon number 1 group, carbon 1, 2, 3, 4, 5, 6. Did I get that right? 1, 2, 3, 4, 5, 6. Yeah. So this is going to be our hexane. And then here for the carboxylic acid, we're going to say hexanoic acid, represented right there as an oic acid. We now have to actually reference the fact that there is a triple bond here, which I actually didn't leave myself space for. So this triple bond is going to be on 4 carbon 4, and instead of hexanoic acid, this is where I made my mistake, hexanoic acid. Again, that's going to reference that triple bond. So 4-hexanoic acid. Moving to something a little simpler, 1, 2, 3, 4, with once again a carboxylic acid here. So this is just going to be a nice little butanoic acid. Butanoic acid. And then to really just shift it up into high gear from there, to really just shift it up into high gear from there, we're going to go ahead and look at this one. 1, 2, I want to use blue for the backbone. 1, 2, 3, 4, 5, 6, 7, 8, 9. With our group right here. Gotta stay consistent. So we have a 9-carbon one. And this one just gets a little weird because we also have those benzene groups, but we'll get to that in just a moment. This is going to be, sorry, nonanoic. Oh, I was doing the oic acids in green. Oic acid, nonanoic acid. But now we have to go ahead and reference these two groups right here. So here we go, red. So we have this structure which we look at as a benzene ring, but because it's not the main thing, we're not actually going to call this a benzene backbone. We're going to call this a phenol, much like we talked about the phenol somewhere up here, way early on, still earlier, over here in 36. We said ethyl phenol, but we're going to instead use that same one here, but you'll notice instead of phenol, instead of the OL that represents the alcohol right here, we're not going to use that terminology. We're going to use phenyl because we can't say benzenyl. Once again, we're using that YL to represent it's a side chain, but you can't attach that to benzene. We don't say benzene benzenyl. We don't do that. We instead say phenol. So this is the correct one. We use phenol, not benzenyl. So I'm going to take this idea, just shift it right here for now as we write our name, because we have 2 phenyl groups on carbon 1, 2, 3, 4, 5, 6, 7, 8. This is going to be diphenyl nonanoic acid. So for this one, we have diphenyl nonanoic acid on the 8 carbon. There it is. Woof, that was a weird one. Moving on to 57. We have quite a few things going on here. Let's start off with our side chain. 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbon, 6 carbon. And once again, a carboxylic acid. I'm now going to just use one color to represent this. So this is going to be hexanoic acid. I think we had a hexanoic acid already. And on this hexanoic acid, I notice that we have 1, 2, 3, 4 methyl groups. 4 methyl groups is going to be tetramethyl. Again, that L representing the side chain, and carbon 1, 2, 3, 4. So we have 2, 2, 3, 4 tetramethyl hexanoic acid. All right. Moving on. On this one, we have a bunch of different carbon chains. This gets quite a little convoluted, but that's okay. We can definitely work from here. And the issue with this one is no matter which way we go, it's going to be the same. So we're just going to pick one as our longest chain. So for this one, I'm going to pick the C5H2 from the top. Doesn't really matter. And I'm going to include this side, our oic acid. That's 5, 6, 7 heptanoic acid. All right. Then I'm going to recognize my 2 side chains. I have a prop and a pent. Pent comes before prop because even though they both start with P, E is before R alphabetically. Because once again, we're back to the alphabetical order. If this is carbon 1, these are both on carbon 2. So we're going to say 2 pentanyl, or sorry, not pentanyl, pentyl. 2 pentyl, 2 propyl, heptanoic acid. 2-pentyl 2-propyl heptanoic acid. All right, moving on to 59. And look at this. It's a benzene ring with our carboxylic acid. And you'll notice, much like with the aldehyde before, where we said benzene-al, we're also going to say benzenoic acid. So over here, we're going to go benzenoic acid. Now, the reason we want to say benzenoic acid is because, once again, a carboxylic acid, no matter where it is, it's going to be on carbon 1, and we have to throw carbon outside of the ring just to make it not in the middle of the chain, because the oxalic acids, the carboxylic acids, are going to be on the outside of a benzene ring, because that's the only way to get an end carbon. From here, we can do our counting. Now, for this counting, I notice our 2 side chains, so I'm going to go and highlight them real quick. We have a propyl group here, and we have a butyl group here. So between prop and but, we're going to say but first. In addition, we're going to count 1, 2, 3, 4, 5. If we counted the other direction, 1, 2, 3, 4, 5, 6, we would have far higher numbers. We would have 3 and 6. In this direction, we have 2 and 5. So I'm going to go with the lower numbers. So starting with but, because B is alphabetically before P, as in prop, I'm going to say 2 butyl. Then I'm going to move to 5 propyl benzenoic acid. 2 butyl, 5 propyl benzenoic acid. All right, moving on to number 60. We are now introducing our nitrogen groups. Those nitrogen groups are part of the amines. So I notice my chain right here, and I notice my amine right here, our NH2 attached to it. Our initial carbon chain only has 4, but. Now this is all single bonds. We have to reference that, butan. And then for this, we say amine, butanamine. You will have to put a 1 because amines can be in the middle or on the end. 1-butanamine shows us that it is on an end. All right, moving to 61. Oh, let's go ahead and recognize our initial 6-carbon ring. This is not a benzene structure. There are no double bonds to reference that, along with an amine group over here, as well as a methyl group over here. So our base is going to be a 6-carbon ring that is cyclohex to reference that, and it's going to be hexamine. Oh, sorry, I'm going to keep my colors consistent. I said amine was green. Hexamine. On that cyclohexamine, we're going to name that amine 1 cyclohexamine. Furthermore, if we go numbering 1, 2, 3, we have a pretty low number for our 3-methyl 1 cyclohexamine. All right. Moving on to 62. Not only do we have an amine in 62, let's go ahead and point that out, but we've got some wild here. We've got a chlorine in the mix. Where'd that thing come from? Well, we're getting just a little bit ahead of ourselves, but that's going to be a halogen. With those halogens, we just kind of put that as a prefix before, such as in this case, it's going to be the prefix chloro. So going through this, starting off with my chain, oops, wrong. 10, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8. Octo. But before the octo, well, let's just go ahead and write it out. octo. There's a couple ways to do this. We have our octoamine. In this case, we're actually going to drop the O because we could write, well, let me write it out first. We could say octoamine, but we don't really like that double vowel. Again, we're always trying to avoid that double vowel. So we're going to say octamine, and we're going to reference that. So in terms of the reference of the IUPAC naming structure, the amine will take precedence to have a lower number than the halogen. So in that case, we would have to name 1, 2, 3. Otherwise, it would instead from the other side be 1, 2, 3, 4, 5, 6. And we don't like that. For the amine, that's going to take precedence. So this is going to be 3-octamine. Now we have to go ahead and refer to that chlorine. Oh, I don't know how that happened. We have to refer to that chlorine, which now must be on the last one, 8-chloro-3-octamine. You could say 8-chloro-octa-3-amine, but I'm not putting that number in the middle. That's my butt. I'm not going to put that number in the middle. All right. Again, you can always put those numbers in the middle. You don't have to. You're going to see it both ways in your IB. It's kind of ridiculous. But with that said, let's keep moving. 63, back to a little bit of normalcy. Whoops, I got the amine in there. We have an amine group right here. And you'll notice, well, this is an O, it's also attached to an H. So that's our alcohol group. Going with our carbon chain, that's 3 carbons. So I'm going to just put prop in there for good measure. Furthermore, this is propanol. So the thing with amines is we can write amine after, but we can also write the prefix amino. And with alcohol, there is no prefix option. With alcohol, the only thing you can do is throw it at the end as an OL. And we can't say aminol. We can't add both suffixes at the same time, so we can only choose one of them. And because the amino group has 2 options, we're going to give the end to alcohol. So we're going to say propanol. Again, you can say propan-1-ol. We're going to give the priority to the alcohol. So we're going to say 1-propanol. Therefore, on the other end, we're going to say 3-amino. 3-amino, 1-propanol. You could say 3-amino-propan-1-ol as well. Again, we can always do that thing in the middle where we say propan-1-ol. Up to you. I'm not going to be upset if you do it one way or the other. Do what makes sense to you. Do what works best for you. Moving on to 64. Look at that. We are now combining so many different things, but not actually. It seems like we have kind of a ketone thing or an aldehyde thing, but actually we bring in a new group by throwing this oxygen amine here in this mix. This is going to be our amide, spelled A-M-I-D-E, an amide, however you want to pronounce it, it's okay with you. And attached to, in this case, a 3-carbon chain. So we're going to say propan. Again, we got to reference those single bonds. Propanamide. And because of the nature of this, C double bond O, single bond nitrogen, it must be at the end. This one will not be in the middle of a molecule. This one will be at the end. All right. Moving forward to 65. Ooh, I recognize a certain structure here. It may be written a little differently, but to me, that looks like a benzene ring. We have 6 carbons with 3 double bonds. That is a benzene. Furthermore, much like with the much like with the aldehyde, much like with the carboxylic acid. On this one, we have our amide group thrown off at the end. Because this is a benzene ring, the only way to make it at the end is to throw it off. That's going to get that priority in the numerical system. But again, because it's the end, it's always going to be our number 1. So this combination right here is, benzene, or sorry, not benzene, benzamide. Oh, I got to switch to colors. Benzamide. But there's one more thing we have to do with this one. I see the BR right there. So we have to reference that bromine. So we're going to say bromo benzamide. And again, that's on carbon, counting from the amide. 1, 2, 3, 4. 4 bromo benzamide. Oof. Keep going. This is going to be a long video, y'all. We have 1, 2, 3, 4, 5, 6. It didn't matter which way I went. On this 6, we have our amide. We also have this ethyl group. The ethyl, we already know is going to be in the front, but just to say with consistency, I'm going to talk about our first hexamide, whatever you want to do. Oof, I even made the mistake right here. We have to reference once again that this is going to be all single bonds. So to reference all the single bonds and also to keep my colors consistent, I'm going to say hexan, and that's going to reference all my single bonds, hexanamide. And then to reference this ethyl group, we already know how to do this. Carbon 1, 2, 3, 4. 4 ethyl hexanamide. Oops, don't need that hyphen right there. 4 ethyl hexanamide. All right. Oof, another big one. Let's get to it. Start off with recognizing our initial structure. It is this nice little carbon ring. Attached to that carbon ring, we see our amide. Once again, this is now not benzene. It is a cyclohex. So we have to reference that cyclohexanamide. So I'm going to reference that cyclohexanamide because I know I'm just going to rewrite hexanamide. I'm just going to copy that over. But this time it is cyclohexanamide. On that cyclohexanamide, we have 2 functional groups in addition to the amide. We have an iodo and we have a methyl. Because we have these 2 functional groups vying for that prefix space in the front, I comes before M alphabetically, so we're going to start with the I. If I go through my counting, 1, 2, 3, 4, 5, 6 is going to come out as 5 for the methyl and 2 for the iodo. If we went in a different direction, it would be 1, 2, 3 for the methyl, 4, 5, 6 for the iodo. That is much higher. So I'm going to instead start with the iodo. So I'm going to say 2 iodo to reference the halogen, the iodine. Then I'm going to go to the methyl, 5 methyl, cyclohexanamide. 2 methyl, 5 iodo, 5 methyl, cyclohexanamide. And I'll start switching colors again because I realized I put the methyl and the amide in red. And so I guess, I don't know, I will underline the methyl and underline the methyl here so you at least can tell the difference. All right, we are going on to new territory. C triple bond N. C triple bond N. That is different than the amide. It is different than the amino. This is what we call a nitrile. This is a nitrile. So we're going to have to reference the fact that this is now something new. Starting with my backbone and making sure to include this carbon that has the nitrile. 1, 2, 3, 4, 5. If I go down, it is also 5. But going down, I'll just keep that as an ethyl group. So how do we reference this nitrile? Well, we just kind of shove the word nitrile at the end. And we do that by writing, our 5-carbon chain, pentane. This would be pentane if it had no nitrile, but because there's a nitrile, we're going to say pentane nitrile, all one word, pentane nitrile. And then we're going to go ahead and add our ethyl, little ethyl group at the end. And we're going to count that ethyl out. That ethyl is on carbon 1, 2, 3. This is going to be 3-ethyl pentanitrile. All right, moving into our weird skeletal format. This one looks quite terrible, but I trust you. But trust me, it is not. I'm going to actually go and recognize this functional group. It's the only one here, and it's a chlorine. So I know I'm going to talk about chloro. Furthermore, if I use that functional group as part of my main chain, I have carbon 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. All right, 7 carbons. And I have a 2-carbon chain, an ethyl group, and a 1-carbon chain, a methyl group. I'm also going to go ahead and just start my counting from this carbon right here, 1, 2, 3, 4, and I don't need any numbers higher than that. So recognizing that 7-carbon chain, I'm going to say heptene, because I'm recognizing the double bond that is inherent, heptene, but I want to actually reference that double bond, so I'm going to say that is on carbon 2. I'm going to say 2-heptene. I also want to make sure I reference that chloro. So if we just do a real quick thought process of what we have chloro, ethyl, and methyl. These are our 3 functional groups. Alphabetically, they go this way. So we're going to start out with chloro. So I'm going to go ahead and say 1 chloro to reference where the chlorine is. Then I'm going to say 3 ethyl. Then I'm going to go and I'm going to use black to represent the yellow. This is going to be 2 methyl. Oh, I'm running out of space. Let me just back this stuff up. 2 methyl. Oh, sorry. I want to actually rewrite this so it's legible. 2 methyl, 2 heptene. 1 chloro, 3 ethyl, 2 methyl, 2 heptene. If you want to clean it up a little bit, a different way to write it would be 3 ethyl, 2 methyl, 1 chloro. Sorry, I'm actually getting this backwards. Let me just change this around. 1 chloro, 3 ethyl, 2 methyl, heptene. I can put that 2 right smack dab in the middle of heptene to reference that, in which case I would be removing this and shoving that next to it. So you don't have to have that 2 there. You can put the 2 right in front of the ene. It doesn't matter, y'all. Either way, just make sure you have all the functional groups. Make sure you're keeping alphabetical order on those functional groups unless certain ones are taking priority, like alcohols at the end, amides at the end, whatever. Moving on to number 70. Let's identify our carbon chain. 1, 2, 3, 4, 5. Thank gosh. Something that is easy. Pentane. Oh my goodness. It's been a while since I've just written pentane. All right. As my functional groups, I have 1, 2 bromines, so dibromo. I have 1 iodine. I know that B comes before I alphabetically, so I'm going to start off with carbon 1, carbon 2, carbon 3. 3, dibromo, to reference the 2 bromines. 2, iodo, pentane. 3 bromo, 2 iodo, pentane. Done. Moving on to the next one, we have this really weird structure. If you can do this one, you can honestly do anything. So let's just jump right into it. So with this one, well, actually, I realize we have to do 71 before 72. Let's get to it. 71. I notice a couple things right off the bat. I notice that I have this cyclical structure right here that is not a benzene. It is missing a double bond. In addition to this not benzene, I have this other weird chain structure that has another functional group on it. So this is the first time we are seeing a functional group on top of a side chain. So when we see this functional group on top of a side chain, we now have to start using parentheses, or as you refer to it, brackets, to represent this individual carbon chain with its own structure, because otherwise we're going to mix our numbers around. And I'll show you what I mean in a moment. As we go to label this, let me actually also indicate the side chain right here, the fluoro. As we go to label this, I'm going to first notice the cyclohex, and this is cyclohexadiene. Cyclohexadiene to reference the 2 double bonds. Because these 2 double bonds are close to the edge, I'm going to go ahead and label these. Now, there's a whole bunch of different ways to label this, but remember that we are trying to go for the lowest possible number. So you could try and label 1, 2, 3, 4, but these are going to take this weird precedent where we want the side chains to have, we want the double bonds to have that numerical priority. So instead, we're going to go 1, 2, 3, 4, 5. That's going to be the lowest possible numbering that we can do. So this is going to be 1, 3 cyclohexadiene. That's our backbone. So now we have to look at this other side chain. If we just identify the side chain as its own thing, we might say pentane, but with the fluoro group. So we might say instead it's going to be carbon 1, carbon 2, so that we can get it. So we might say 2, got to give myself some space. We might say 2 fluoropentane, and that would be fine. That is what just that side chain is called on its own. But now we have to recognize that this is in fact a side chain. So instead of pentane, we're going to say pentanyl. Because remember, that's going to reference that this is a side chain. Furthermore, this is a side chain off the 5 carbon. So we have to reference that this is a 5th carbon side chain. And I'm still going to go ahead and do that. So the issue here is we want to say, because this is a side chain on the 5th carbon, we want to say 5,2-fluoropentanil. But that's where the problem is. We can't do a 5 dash into a number, because which one is referring to the fluoro, which one is referring to its position. So to solve this, this is where we use the brackets. This as a bracket is a whole as a side chain. So this 5 is referring to everything in the brackets. It's our way of separating. It's kind of like in math when you put brackets to represent a separate part of the equation and kind of isolate a certain thing. So these brackets represent its own side chain with its own ideas in it. So we're going to take that to the extreme on 72. 72 is difficult because we have to recognize, first off, the longest chain. We have to recognize how this chain interacts with other things, and we have to recognize what functional groups are functional to the main chain and what functional groups are part of another side chain. So I go ahead and I'm counting. I'm trying to do two things. One, I want to get these double bonds in my main chain. If I get these double bonds in my main chain, I can say diene, much like I did with the other one. I don't have to reference the double bonds anywhere else. Double bonds like to be referenced as the "-ene" suffix at the end of a main chain. So I'm really going to try and reference those double bonds. So as I build my side chain, I want to make sure I include them. This kind of limits my movement here. I can go here and then up to get the most carbons I can. Furthermore, I can go here, up, and down to get the most carbons I can. So this is what I'm going to define as my main chain, and I'm just going to redraw that so it's nice and neat. Boop, 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 boop. All right. And if I go ahead and count, that is going to be 10 carbons. Carbon 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. I'm actually going to keep that numerical system because I really want to reference them in this order. Again, the reason I'm choosing this numerical system is it puts the double bonds from this decadiene in the earliest positions, being 3, 6 decadiene. So that is how I'm going to end my molecule, and I'm going to move this down here so I really have room to build off of. All right. From this decadiene, I have quite a few different groups. I'm going to start off with the simplest ones. The simplest being I have a methyl group here, a methyl group here, and a methyl group here. Methyls being with the suffix or being starting with the letter M usually indicate that they're going to be at the end of our alphabetical order because we have, for example, a fluoro. Oh, I'm going to change the color. We have a fluoro attached to a prop. We have an iodo attached to a bute, and we have a chloro. So we have chloro, bromo, fluoro, and meth. Those are all the beginning things. Let me just keep that down. I'm going to kind of write it, I guess, somewhere on the side, but I don't really have room. We have chloro, we have fluoro, we have bromo. Oops, I forgot to highlight that bromo. We have chloro, fluoro, bromo, and iodo, and then also methyl. So I have these 5 different side chains or side groups that I'm going to have to attach. And once again, I'm going to try and do this in alphabetical order. So doing in alphabetical order, I'm going to do bromo, chloro, B, C, D, E, F, fluoro, iodo, meth. So the reason I'm doing this in this order is because I kind of want to work backwards from my last statement, which is the decadiene. So I'm going to go ahead and tackle the meth. I have 3 methyl groups. 1, 2, and 3. So this is going to be trimethyl. And using my numbering system, I have 2 on 2, and 1 on 8. So it's going to be 2, 2, 8, trimethyl 3,6-decadiene. So my methyls are done. I don't have to worry about looking at my methyls. All right, working backwards, I now have to look at my iodo group. So I'm going to use, let's say, red to indicate this iodo group. So now that I'm doing it, let me just re-highlight it in red. Oops. This iodo group is its own side chain, such as the one before we had 2-fluoropentanil. This is now going to be, let's use red, 1, 1, 2, 3, 4 carbons. This is going to be iodobute, and this is on the first one. So we have 1 iodobutyl, 1 iodobutyl, and because this is its own thing on carbon 6, it's going to be 6 1 iodobutyl dash. All right, I don't have room to do one long chain, so I'm going to do it on 2 rows, maybe even 3 or 4. So far I have 6 1 iodobutyl 228 trimethyl 3,6-decadiene. Oh, so far so good. Iodo's done. Let's go ahead and cross that out. Now moving on to next in line are fluoros. Let's go ahead and change color. Gosh, I don't even know what color to use. Let's go with purple. Let's get a highlight out. Let's go with purple. So I said I'm on fluoro. This fluoro is on carbon 1, carbon 2, carbon 3. This is a propyl. This is going to be propyl. Propyl. And this is again on carbon. It's going to be on the first carbon. I will order those 1 fluoro propyl. And let me actually get rid of that. Let me rewrite this so it's a little nicer. Fluoropropyl. 1 fluoropropyl. Again, we need parentheses because this is on carbon 4. 4 fluoropropyl. 6 1 iodobutyl 228 trimethyl 3,6-decadiene. Fluoro is done. All right. Now we just have to deal with these last two, and I'm going to do them both in black. We know we have to do chloro next. Chloro is pretty simple. It is just chloro. Whoops, that's not even how you spell it. I said it's simple. Chloro. It is on the first carbon, 1 chloro. It is not its own side chain. It is just a single chlorine, 1 chloro. And lastly, we have bromo. It is on the 8th carbon, 8 bromo. And there we have it. 8 bromo, 1 chloro, 4 1 fluoropropyl, 6 1 iodobutyl, 228 trimethyl 3,6-decadiene. We did it, y'all. That's, I think, the hardest one on this, but we got it. We have survived. So how about a break into something easy? And I'm actually going to go ahead and see if I can move our little tracker. I'll just kind of overlay it right there. Oh, we survived. Moving on to this new one. Nice, easy benzene ring. Easy. Benzene. I'm almost done. The only thing is that on this benzene, we've got something weird, kind of, not even anymore. We have an iodine. 1 iodo benzene. But if you want to be, oh, sorry, no dash. But if you want to be specific, everywhere you put it is going to be 1. So screw it, iodobenzene. Because it doesn't matter where we put that iodine, it's going to be the same. Again, a little bit back to normalcy. Let's go ahead and recognize that we have 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbon, 6 carbon. Ooh, these seem easy now. Hexane. But attached to that hexane, we've got this nice little methyl group. And it's attached to carbon 3. So 3-methyl hexane. Done. Oh, would you know? Coming up next, we have a nice little ketone. We can say 2-butanone or butanone because we have 4 carbons. It's going to be butanone, 2-butanone, or you know what? Let's go wild. Butanone. Either or. You make up your mind. These should seem pretty simple by now. 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbon, 6 carbon, 7 carbon, 8 carbons. It looks like we are on a wild ride of crazy stuff, but really, we just have our octane. No double bonds, no triple bonds. I notice that we have, I notice we have a methyl group, an ethyl group, and a chlorine, a halogen. So let's just give ourselves the lowest possible numbers. Carbon 1, 2, 3, 4. All right. If I organize these up alphabetically, chloro, eth, meth, methane is going to be close. Meth is going to be close to the octane. And then on this one, we have our ethyl up next with methyl in the, chloro in the front. This is already alphabetical order. So let's say dimethyl octane. We're going to reference the number they're on, 2,3 dimethyl octane. Let me just scooch myself over so I have some room. Up next is our ethyl group. We're going to do that in red. 4 ethyl, 2,3-dimethyl octane. And lastly is our chloro group. We did that in purple. 3 chloro, 4 ethyl, 2,3-dimethyl octane. All right, moving on. Something nice and simple like another benzene ring. Let's just go ahead and recognize what we write. Benzene. This benzene has 2 things attached to it. Coincidentally, they're the same. 1 ethyl, 2 ethyl. Sounds to me like a diethyl. They are specifically on carbons 1 and 2. Oh, I can't write that. 1, 2 diethylbenzene. Because we do have to note them. I guess you could say 1, 6, but that's too high of numbers. Now onwards to 78. Oh, let's get our highlighter out. I notice a 3-carbon chain. I notice a, oops. I notice the structure that we haven't actually covered yet. And then another carbon. Actually, let's go ahead and a green and a green. We are on to something new. For this one, we have to recognize that this almost looks like a carboxylic acid, but it is not, because we have in between where we would have a hydrogen to make the oic acid, we actually have another carbon chain. So with this compound, we are going to use the suffix for esters. I used red, O8. O8 is going to append to the largest carbon chain, specifically the carbon chain, not the largest carbon chain, the carbon chain that is bonded to the double bond oxygen, single bond oxygen. which in this case is a prop. So propan, oh wait, propan, AN referencing the fact that it's only single bonds. Then, if there's anything attached to that prop, we're going to name it normally. In this case, we have a methyl group. I'm actually going to go ahead and change my highlights. The other side of the methyl group, or the other side of the ester group, is going to be differently named. So this normally would be naming from the ester 1, 2, 2 methyl propanoate. The last thing we have to do is reference the methyl group on the other side, or whatever the carbon chain, the hydrocarbon is on the other side. In this case, it is a meth. In fact, it's methyl to reference the side chain aspect. So methyl space 2-methyl propanoate. It is 2 words, methyl space 2-methyl propanoate. All right, moving back to 78 because I skipped it. My apologies. I notice our longest carbon chain. It is made of a couple carbons. I also notice this methyl group, and I also notice this double bond. So going through this, I have 1, 2, 3, 4, 5 carbons. Pent-ene to reference the double bond, and that double bond is on the first carbon. 1 pentene. I should actually change my colors. 1 pentene. And then I'm going to reference that methyl, 3 methyl. 3 methyl, 1 pentene. Easy peasy. All right. Or 3 methyl pentuanene. Doesn't really matter. All right, moving on to 80. We have avoided esters again. Let's go ahead and recognize our benzene ring with a methyl group and a bromo. Bromo comes before methyl, alphabetically speaking. B comes before M. So we're going to go ahead and write methyl benzene. That methyl is what's attached to the benzene. It's going to give that the numerical superiority, hierarchy, whatever. 1 methyl benzene. Therefore, the bromo is 4 bromo, 1 methyl benzene. Done and done. Moving on to the next one, identifying the longest carbon chain. There's a couple ways to do it. I'm using this one. Oh, sorry. I forget that I use blue. 1, 2, 3, 4, 5, 6 carbons with a triple bond with a ethyl and with a, what color did I not use? With a methyl. All right. So identifying first the 6 carbons with the triple bond, hexine. Give that the 1 hexine. Oh, sorry, that is not 1. My apologies. That is 2 hexine. Can't count. Using that numbering system, 1, 2, 3, 4, 5, 6, we can go ahead and fill out the rest. From the 2 hexine, we have methyl and ethyl. Meth is alphabetically after eth, so we're going to go methyl. We'll reference that methyl. 5 methyl, 2 hexine, and now we have to reference the ethyl. 4 ethyl, 5 methyl, 2 hexine. All right. Moving on to 82. Once again, I'm going to recognize our chains. 1, 2, 3, 4, 5 carbons. In addition to these 5 carbons, I notice an HO, CHO, that is an aldehyde. That has to be referenced at the end. There's no other way to do it. So 1, 2, 3, 4, 5. This is, oops. pentanal. Pentanal. Nice and simple. Moving on to 83. 1, 2, 3, 4, 5, 6 carbons and OH and double bond O. That is a carboxylic acid. That is going to therefore be, wrong colors, hexanoic acid. You know, we sprinkle in the hard ones and the easy ones all together. And we're almost done with all of these. All right, moving on to 85. I want to include that double bond in my carbon chain. I also notice I have that nice little ether, or sorry, not ether, ethyl group, so 2 carbons, which makes it part of the main chain. I'm also going to go ahead and recognize 1 methyl group, 2 methyl group, 3 methyl groups. Recognize the double bond, and therefore I'm also going to name from that double bond 1, 2, 3, 4, 5, 6. So 2 ene, just getting that out there. 1, 2, 3, 4, 5, 6. 2 hexene. All right, so what do I do with this 2 hexene? Well, I've got 1, 2, 3 methyls, and that is on the 2, 4, 4 trimethyl 2 hexene. All right, moving on to our last one. Oof, we almost made it through. Right off the bat, we have an O smack dab in the middle. Because of that O, we have to then recognize that this is 2 separate chains separated by an oxygen, meaning that we instead have an ether. So we're going to use the term oxy, something oxy. And we're going to put that oxy probably on our ethyl group. On the other thing, the longest chain I can see is 1, 2, 3, 4, 5. Oops. 1, 2, 3, 4, 5. So let me go ahead and also get our last chain right here, the methyl group. All right. 5 carbons, that is pentane. All right, attached to our pentane, we have, if we had to number this, I see that we have carbon 1, 2, 3, 4, 5. If we did it the other way, it would be carbon 3 and 4. So I'm going to say we have 2 methyl pentane. Attached to the 2 methyl pentane, we have an ester group. That is going to be ethoxy, and that is on carbon 3 of our pentane. 3-ethoxy, 2-methyl pentane. All right, hopefully this whole section didn't absolutely break your entire brain. If it did, take a pause before we go on to our next section. So for this section, we're going to have to start drawing. So what I'm going to do is add a new page in here, and I'll try and put all our answers on this one. But let's really just figure this out. C5H12, this is number 87. C5H12. What I immediately recognize is because H is 2 times plus 2, the carbons. I can tell that this is going to be all alkanes, all single bonds. That's the only way to have it. So looking at that, I think the easiest structural isomer, structure meaning we're only changing the orientation of the bonds, is going to be 1, 2, 3, 4, 5, pentane. All right, if we instead make it 1, 2, 3, 4, and then throw one carbon off the end, that is going to be 2-methyl butane. With 2-methyl butane, it actually doesn't matter if we take this guy and move it over here. That's still 2-methyl butane. So this actually changes both variants. If we instead put it at the end, we're back to pentane. So we already recognize that that is the only methyl structure we can put with only a single methyl. So butanes are now covered. Moving over to a 3-carbon chain. Whoops. 1, 2, 3. And now we add 1-methyl here, 1-methyl here. This would be 2, 2, dimethyl propane. And we can't actually get shorter than that, so that's it. All the structural isomers are right there for number 87. 88. That was 87. Let's now go to, I'll use blue, 88, which is draw all the structural isomers of C5H10. C5H10. Now that we only have 2 times the carbons, I recognize that we must have 1 double bond. This specifically said structural isomers. And because we're doing only structural isomers, it becomes pretty simple to just do exactly what we did before. 1, 2, 3, 4, 5, and we can put the double bond on this end. And with the double bond on that end, we just have 1 pentene. We can move the double bond over. We can move it over to this, whatever. It's not going to duplicate. If we put the double bond on this end, it's still 1 pentene, so we're not going to do that. We can move it to the middle. If we put it on the second carbon, if we go 2 pentene, 2 pentene, regardless of where we put the double bond then, we could again move it here. That would still be 2 pentene. We can move it here. That would then be 1 pentene. So that's the only way that we can put it right over there. So we can go ahead and now do the exact same thing we did with the first one where we had 2-methyl butane. We're going to go ahead and make our butane. Put the double bond right there. And we cannot, we can, but there's only one option for this. We can put the methyl group here, or we can put the methyl group up here. We'll do it down here first. So in this case, we have 1 pentene, 1 butene, or but1ene, along with, and I'm going to now identify our methyl group in a different color, 2-methyl 1-butene. I can then go ahead and make our 1-butene structure again, but this time throw our methyl group up there. And this is still going to be 1-butene. And we have now 3-methyl. 3-methyl 1-butene. All right. But this is where it gets a little complicated. You would normally think, well, why don't we just go to a prop? Oh, you know what? Actually, there's one more on this. I'm looking at it now and I realize I haven't moved the double bond on our butene. Sorry, here we go. We could also put the double bond in the middle, which would be 2-butene. And if we throw this methyl group here, it is exactly the same as if we threw it here. We can just rotate this molecule in 3-dimensional space. And regardless of how we do it, this is 2-methyl 2-butene. All right. Moving on to what we did before, we went to prop and then had one here and one here. But the issue is we cannot do that because if we put a double bond here, we cannot, I should use a different color. We cannot add another bond to that central carbon. That's already 4. There is no propene that also has 2,2-dimethyl. We cannot have that because that is now too many bonds for the carbon. We put it here, that would be 5 bonds. That's too many shared electrons. This is not allowed. So that is all these structural isomers for 88. 89. We have quite a few for 89. This is going to be C3H8O. So I'll use black. C3H8O. C3H8O. Something quick to notice is that 3 times 2 plus 2 is equal to 8. So this is going to be an alkane. We're only going to have the anes present. So for this one, we can very quickly see that because there's only single bonds, we're not going to have aldehydes. So this is alkanes. So we're not going to have no aldehyde, no ketone. Whoops. Ketones use double bonds. We can't have carboxylic acids. We can't have, because that takes 2 oxygens. We can't have esters because, again, that takes 2 oxygens. So we're not going to have aldehydes or ketones, but we will have ethers and alcohols. So we can have both ethers and alcohols. So we only have 3 carbons. So we can have one, which is just one propanol, one propanol. We can also put that in the middle, which is 2 propanol. The other name for 2 propanol is also isopropyl alcohol. You may have heard that before, but really we're just going to call it 2 propanol. Isopropanol. Iso just meaning in the middle. But we can also do our ether. So that's both our, that's both of our alcohols. But we can also do our ethers. So for our ether, we will have a carbon, an oxygen, and then CH2, CH3. I'm just kind of wilding it with this diagram, but we're going to say methoxyethane. So I'm going to identify the longest chain, just like we used to in the previous one. I identify our side chain. I identify our ether. So let's go ahead and label this. This is going to be ethane. This is going to be the oxy part. And this is going to be the methoxyethane. Or if we want to go back to the other way of doing it, methyl, ethyl, ether. I think we did that once, but that is also a name. Either way, it's okay. Moving on to number 90. Draw all the structural isomers of C4H9F. All right. 90, I'll use blue again. C4H9F. Now this F kind of takes the place of one of the hydrogens. So this is kind of almost like having 10 hydrogens, which in this case means we're doing alkanes, no double bonds. All right, so let's go ahead and just make some alkanes. Here's our butyl structure, and we'll put a fluorine on one end. Here's our butyl structure, we'll put a fluorine, we'll put a fluorine on one end. And if we put the fluorine either on the other end or the other middle aspect, it's all the same. So for these two, this is 2-fluorobutane. This is 1-fluorobutane. And I think I'm going to run into more questions, which is our answer sheet. So I'm going to add another page. I'm just going to add 2 pages in case I need them. So 2-fluorobutane, 1-fluorobutane. We can also make our propyl structure with 1 methyl group, and we can put the fluorine here. But if you look and we put the fluorine here, it's the exact same structure. So it doesn't really matter where we put it. Or sorry, oof. Let me redraw that because I realized I made a mistake. So that's our propyl structure, and we attach a fluorine. But again, if we make our propyl structure and then attach a fluorine, it's the same thing. Because again, these molecules rotate in 3-dimensional space. So with that propyl structure, with the fluorine, this is going to be 1-fluoro, 2-methyl propane. Let me actually make this 1 word instead of 2 words. 2-fluoro, 1-methyl propane. I'll highlight some stuff just so we have it. 1-fluoro, 2-methyl propane. And regardless of which group you look at as a methyl, it's the same exact thing. And then the last isomer, because it did give us a hint saying there are only 4, we could do, we could do our propyl, our methyl propyl structure, our 2-methyl propane structure. But we could also attach the fluorine to that central carbon as well. And in this case, we would have 2-fluoro, 2-methyl propane. And that also works. 2-fluoro, 2-methyl propane. All right, moving on to 91. We are almost done, y'all. Draw the structural isomers of C7H16 with a carbon chain of 5 atoms. Therefore, these are all going to end in propane. So C7H16, and then we are limited to 5 carbon chain backbones. Whoa. Backbones. So we're very limited. Again, this is 2 times plus 2. So I know these are all going to be alkanes. All single bonds makes it nice and easy. And we know that there's only going to be 5 isomers. So I'm just going to go ahead and draw 5 structures. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. These are all my 5 carbon chains that I'm just going to kind of make modifications to. So these are all going to end in the word propane. So let's just kind of try and figure out the best way to do this. I only have 2 more carbons to add. So what if I add 1 carbon here and 1 carbon here? All right, then I'm going to add 1 carbon here, 1 carbon here. 1 carbon here, 1 carbon here. All right. So those are 3 different ones right there just by putting dimethyl groups around. But what if I put an ethyl group? Well, if I put an ethyl group here, I actually end up making a 1, 2, 3, 4, 5, 6 carbon chain. And we're limited to only 5 carbon chains. So in that case, I can only put it here. And therefore, regardless, I have a 5 carbon chain. Ah, but that also gives me one more idea. What if I put the dimethyl here? And that's different than all those. I can't put it on this end because that would be this, then these two would be the same. So it has to be in the middle. All right. So let's kind of just loop all the similarities together. This is going to be dimethyl pentane. And I'm just going to duplicate that a couple times. Duplicate, duplicate, duplicate. These are all dimethyl pentanes. This one's going to be instead ethyl pentane. Now all I need is the new numbers. This one is going to be 2, 2 dimethylpentane. This is going to be 2, 3 dimethylpentane. This is going to be 2, 4 dimethylpentane. This is going to be, in this case, actually, there is no other way to do it, but we're still going to go ahead and number 3 ethylpentane. And then this one's going to be 3, 3 dimethylpentane. There we go. There's all our isomers for the C7H16. All right, moving up to 92. Draw all the structural and geometric isomers of C4H8. Geometric isomers is something we haven't fully discussed yet, but hopefully I'll help you identify them here. Geometric is purely based on shape, while structure is based on the bonds and such. So we're going to have different shapes. C4H8. This is now, we're on 92. C4H8. And once again, it is only 2 times, so that means we have 1 double bond. Or that could also be 1 cyclical structure. So it's going to be 1 double bond or 1 cyclical. And this is where we get into the idea of we have geometric isomers, which means the shape as well as with those geometric isomers, sorry, that's still structural, but with geometric, we're going to start identifying things called cis and trans structures. You may know these prefixes. Yeah, cool. I have another page. Let's just start with the basics. So 1, 2, 3, 4. 1, 2, 3, 4. Nice and easy. We have 1 butene, 2 butene. Easy peasy. But this isn't actually correct. Our second one isn't 2-butene. It is what's known as trans 2-butene. Because this double bond actually locks the structure in place. We could theoretically have this structure. And this would be cis 2-butene. And these are what's known as geometric isomers. Cis and trans structures come from this kind of locked orientation that a double bond provides. Because while single bonds can kind of rotate freely, double bonds, not so much. We'll kind of go over this with molecular model kits in class, and I won't put this on the next summative you have, but it'll be on the one after that. But these are our 2 geometric isomers for this. On the other hand, 1-butene isn't going to have a cis or trans structure because regardless of which way that carbon bends, the other end has 2 hydrogens. It only happens when you have a double bond and then something different on all 4 ends. So if you have these 2 ends are different and these 2 ends are different, you can actually go ahead and switch those where you have something here, something here, something here, something here. The structure is locked into place. So this would be the cis structure where it's the same thing on both sides. And this would be the trans structure where it's different things. You'll notice these 2 are different while these 2 are the same. So cis and trans structures. All right. With that there, these are the 2 geometric isomers, but that's from the double bond. Those are all the double bond versions we can get. Now we have to go into the possible cyclical structures of butene. Well, one is just a square. This is just cyclobutene. Another cyclical structure is a triangle with one carbon coming off, and this would be 1-methyl cyclopropene. Sorry, I said butene, but I should have said butane. For anyone yelling at their computer, I apologize. Cyclobutane, 1-methyl cyclopropane. All right, those are all the structural isomers for 92. I think it said there should be 6. We only have 5. What am I? All right, we actually have one more double bond structure. We take our standard prop, we just throw a double bond there, and this is going to be 1 propene with a 2-methyl. 2-methyl, 1-propene. That's our methyl group. And so 2-methyl, 1-propene, and that is 6 structures. We got there. All right, moving on to 93. I am absolutely going to need another page. Bear with me. Let's just add a couple more pages in case. All right. Number 93. Draw all the structural and geometric draw all the structural isomers of C6H3F2Cl. Then include a benzene ring and name them. There are 6. One more time, C6H3F2Cl. C6H3F2Cl. And we've been told that all of these include a benzene ring. So, number 1, I'm gonna draw, oh my gosh, I'm gonna draw a benzene ring. Let's see if my iPad can recognize a hexagon. Perfect. And I'm just gonna put the circle in there, identifying a benzene ring. All right, and I know that there are 6 isomers. So in this case, I'm gonna make 6 of these. 2, duplicate. That's gonna bug me. Cool. Here are 6 benzene rings. The beauty of benzene is that each carbon has already made 3 bonds. 3 bonds. So it can only make 1 more. So with that in mind, there's a couple ways we can do this. We know we can't put 2 hydrogens or 2 things on each one. Each one normally just has 1 hydrogen. So really what we're doing is messing around with the fluorines and carbons. And we're trying to make sure we don't repeat. So we'll put a fluorine and a fluorine next to each other. We'll put a fluorine and a fluorine 2 away from each other. We'll put a fluorine and a fluorine 3 away from each other. And any other variation is actually going to turn out, every other variation is going to actually be the exact same in the other way. If we put a fluorine and fluorine 2 away from each other on the other side, so if we, for example, do fluorine and fluorine, well, these are the same thing. So I'm not going to do that. But I'm going to go ahead and add the chlorine and see what changes. I could put the chlorine here. That's something new. Right next to it. I could put the chlorine in between. That's something new. I could put the chlorine in between here. But we'll actually make some new structures with this. In this case, we can instead change the position of the chlorine and fluorine and try not to repeat ourselves. So for the top one, I'm going to, once again, put the fluorine and fluorine next to each other. But now I'm going to put the chlorine one away, which coincidentally can't make a new structure if I put the chlorine here because those would be the exact same. So when the two fluorines are together, there's only one other position the chlorine can be in. All right, on the next one, I can once again put the fluorine and fluorine, and now I can put the chlorine over here. I realize I may also instead, with that same one, go fluorine, fluorine, and I can put the chlorine over here. If I, however, move this chlorine to this side, then it'll be the same thing as that one, so I can't do that. With the fluorines on opposite ends, if I move the chlorine here, it's the same thing. If I move the chlorine to this side, it's the same thing, and to this side, it's the same thing. So with these isomers, you have to start thinking about all the different structures that it could make, and really whether or not changing position is different or the same. It is kind of difficult sometimes to see, and three-dimensional shapes help us do that, which we'll try and build some in class. So let's go ahead and name all of these. For the lowest numbers, I'm just going to go ahead and say 1-chloro, 2,3-difluorobenzene. Honestly, I'm going to keep this difluorobenzene. I'm actually going to keep all of this. The only thing that's going to change, because chlorine C comes before F, so chlorine's always going to be the same. So I'm going to keep the same structure. Some number chloro, difluorobenzene. So all of these are going to be the same thing. The only difference is going to change the numbers. So I'm going to go ahead and just duplicate this 6 times, so I don't have to keep writing. I know you can't do that. And then erase our numbers. All right, and then I'm going to fill these in with new numbers. Moving on to our second structure right here, where we have the chlorine right in the middle. Once again, we're going to go 1-chloro. And actually, I don't know why I erased 1. We're always going to name these chlorines 1 for continuation of giving that chlorine that priority. It's alphabetically first, whatever. And then in this case, that means it's 2,6-difluoro. In this case, we're going to have 2,5-difluoro. In this case, we're going to have 1, 2, 3, 4, 4-difluoro. In this case, we're going to have 1, 2, 3, 4. So this is going to be 2, 4-difluoro. And then lastly, in this case, we have 1, 2, 3, 4, 5. This is going to be 3, 5-difluorobenzene. All right. We have done number 93. On to 94. We're almost done with this whole thing. All right. For 94, what I think I'm going to do is I might just copy this selection. Well, I'm going to pause it so you don't have to see all this. I'll be back in a sec. All right, welcome back. I just have this here so that I don't have to go ahead and re-scroll up and down every single time. Starting with A, 1 pentene, 1, 2, 3, 4, 5. 1 pentene, done. B, 4-methyl hexanoic acid. Hexanoic, this is going to be 6 carbons. 2, 3, 4, 5, 6. On this last one, double bond O, single bond OH, that's hexanoic acid. And then if we're counting from the anoic acid, carbon 1, 2, 3, 4, we have a methyl group. All right, that's B. Oh, sorry, that was G, my bad. I went across, but I will not do that again, hopefully. B. 2-methyl 3-heptynes. This is hept. 2, 3, 4, 5, 6, 7. On that, we have a triple bond on the third carbon. 1, 2, 3. Now, I actually will have to redraw this because a triple bond creates a straight shape. So it's actually more like 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. That's more like it. All right. If you're using the skeletal structure, you need to get that geometry right. So just be careful. And then on that, we have, if this is the third carbon, we have a methyl group on the second carbon. That is 2-methyl 3-heptyne. All right, C. 3-ethyl 4,5-dimethyl hexane. So hexane. 1, 2, 3, 4, 5, 6. Hexane. 3-ethyl. 1, 2. Ethyl group. All right. 4, 5. 4, 5. Dimethyl. Done. If you need numbering, 1, 2, 3, 4, 5, 6. Don't number it when you're drawing it out. Oh, you know what? I made a mistake here. The question says draw the structural formula. It's not the skeletal formula. So I'm just really quickly going to do structural. CH3, CH2, 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 and I made a mistake. This is CH. I'm just counting the hydrogens. Or, sorry, my goodness, another mistake. This is not a structural formula because I didn't put the bonds here. 1, 2, 1, 1, 1. There we go, structural formula. For this one, CH3, single bond, CH, single bond, CH, sorry, I'm just counting my carbons, CH3, single bond C, triple bond C, single bond CH2, 1, 2, 3, 4, 5. Single bond CH2, single bond CH3. This is heptyne. 1, 2, 3, 4, 5, 6, 7 with a methyl group. Cool. Moving on to the next one, I'll change to green. CH3, CH2, bonded to CH, which bonds to C2H5. That's going to represent our ethane. Oh gosh, I should not be cutting corners. It should be CH3, nope, not even CH3, CH2, CH3. When you do it fast, you make mistakes. Bonded to a CH, bonded to a CH3, bonded to a CH, bonded to a CH3, bonded to a CH3. Counting 1, 2, 3, 4, 5, 6. That is our hexane. All right, A, B, C, D. 2-ethyl 1-pentanol. All right. We're going to do our pentanol. So that's going to be O, HO. I do HO to represent that we have the oxygen bonded, and it's going to be on the 2-ethyl. So we get a CH2. Then we get a CH, CH2, CH3, CH2, 1, 2, 3. This is a 5. CH2, CH3. That is our pentanol. All right. Moving on to D. Or that was D. Moving on to E. 3-bromophenol, phenol, OL. That's going to represent our benzene ring. So we have CH. This is cyclical. We can't actually represent it like this, so we have to instead go C, C, H, OH. It doesn't really matter where we put the double bonds as long as it's alternating. CH, CH, and I'm going to make some changes. CH, I'm just drawing my benzene ring first. CH, alternating double bonds. And then this was actually 1, 2, 3 bromo. So instead of an H somewhere, I'm going to do C, BR. All right. Honestly, I like the skeletal structure for the benzene ring, so I would prefer just writing this. I think that's much cleaner, or sorry, benzene ring. I think that's much cleaner. So I prefer this. EF. 3366 tetraethyl 4-octine. All right, that 4-octine is kind of where I kind of want to start. C triple bond to a C. And before that, I'm going to have a 1, 2, and 3. So I'm going to have 3 before that. Specifically, we have 3366 tetraethyl. Okay. So this is going to be CH3. This is going to be CH2. On the third carbon, I have 2 ethyls, CH2, CH3, CH2, CH3. And then on the sixth carbon, I also have 2 ethyls, CH2, CH3, CH2, CH3, CH2, CH3. All right, there we go. Moving on to G. I'm going to go back up because I already have G here. And so I'm going to start off with my carboxylic acid just so I know the amount of room I need to have. Double bond O to a C with a single bond OH. Attached to that, we also have a CH2. I'm here. Then we have a CH2. I'm here. Then we have a CH. Attached to that, we have a CH3. Then we have a CH2. Then we have a CH3. There's G, H. Two, 3-dichloro, 4-ethyl, 2-hexene. I'm going to start off with the 2-hexene. 2-hexene, we have a double bond on the second carbon, so we have a single carbon. Do we have anything before that single carbon? No, we have no ones. But on that second carbon, we have a 2 and a 3. So we have a chlorine on the 2 and a chlorine on the 3. Okay, so a chlorine on the 2 and a chlorine on the 3. Now we're not given cis or trans, so I actually don't know if that chlorine is up or down. That would represent trans, that would be 2,3 trans dichloro or trans 2,3 dichloro, but they don't say that, so we're not doing geometric isomers. But we have a 4-ethyl. So let me go to the fourth carbon. On that carbon, we have CH2CH3, 4-ethyl. And then this is, again, hex. So I'm going to do 2 more carbons, CH2, CH3. And then I'm just going to fill out, this has to be a CH3. There's nothing else bonded to it. There's nothing else bonded. It's filled up with carbons. There's H. I. Moving on to I, 1-methyl-2,4-dinitrobenzene. All right, let's start with a benzene. There's a benzene. On that benzene, we have 2,4-dinitro and 1-methyl. I'm actually going to throw that methyl first because it has 1. I want to orient myself. CH3. If that's 1, I like to go clockwise. 2 and 4. Dinitrobenzene. Dinitro is going to reference NO2. NO2, NO2. So to me, that looks like the proper molecule. Just going to double check that I got it all. 1-methyl-2,4-dinitrobenzene. Yeah, okay, J. We've almost made it through. 3-ethyl-2,3-dimethyl-2-pentanol. This is 2-pentanol. So I'm going to start off with a pentane backbone that has an OH, an alcohol, on the second carbon. I think I'm just going to go ahead and draw my carbon backbone. 1, 2, 3, 4, and 5. And I'm leaving space to put hydrogens. I'm orienting myself with this OH attached to the second carbon. In addition, I have a methyl group on the second and third carbon. I have 2,3-dimethyl. So I'm going to go to the second and third carbon and draw a methyl group. Second carbon, CH3. Third carbon, CH3. All right. In addition, I also have an ethyl group on the third carbon. 3-ethyl. Ethyl group on the third carbon. CH2, CH3. All right, and that was all of them. So carbon at the end has CH3, carbon at the end has CH3, carbon not at the end, kind of in the middle of CH2. Every other carbon has 4 bonds, no hydrogens necessary to fill it out. We are on K. Second to last one, we've almost made it through. Heptanone, 3-heptanone. We have a ketone on the third carbon of a heptane structure. So I'm going to draw a heptane structure. C, 4, 5, 6, 7. On the third carbon, I have a ketone, double bond O. All right, that's 3-heptanone. I also have a methyl structure on the fourth carbon. On the fourth carbon, methyl, CH3. All right, I've taken care of the 3-heptanone, taken care of the 4-methyl, and on the fifth carbon, I have 5-chloro. All right, fifth carbon, I have 5-chloro. All right, I'm just going to fill in the rest. H3, H2, H, H2, H3. There we go. Moving on to the last one. HIJKL, sorry. I am almost brain dead from doing all of this in a row. L, 3-phenyl, 1-propyne. All right, so I recognize 2 things. One, I see phenyl. To me, that's the phenyl represents a benzene, but because it's YL, it's going to be a side chain benzene. It's side chain benzene on a propyne. So I'm actually going to go ahead and just start off with the propyne. Carbon 1, carbon 2, carbon 3. It's propyne, and it's 1-propyne, so I'm just going to throw a triple bond. Doesn't matter which side, but now this must be carbon 1, this must be carbon 2, this must be carbon 3. On carbon 3, I have a 3-phenyl. So on carbon 3, I have phenyl. So that's just a benzene ring attached to it. So let's go ahead and do a benzene ring. That is a terrible benzene ring, but you know, we're on the last problem. Lastly, I'm going to fill in the hydrogens. This carbon can have one more bond. This carbon can have two more bonds. And that's it. We've done it, y'all. Congrats. You've gone through it all. You can check your answers if you want. I'm going to upload this, watch it in parts. Who cares? Scrolling back to the top, 14 pages in. Congrats. You made it. We're done.